Okay, so what we want to do now is to evaluate the Hamiltonian. And one of the reasons why I want to evaluate the Hamiltonian is that this is going to allow us to calculate energies of various states in the theory. And the other thing is, you'll see for the first time some infinities arising in quantum field theory. Actually, this will be quite a harmless infinity to fix, but it's going to arise for the same reason that infinities always arise in quantum field theory, and that's because we're dealing with a system with an infinite number of degrees of freedom. So if we want to evaluate the Hamiltonian, well, we want to integrate over all of space with the Hamiltonian density. That's curly h that I've written up here as a function of x. And what is curly h? Well, it's 1/2 pi squared plus 1/2 gradient of phi dotted into gradient of phi plus 1/2 m squared phi squared. So let's remind ourselves of just a few formulas. So first of all, what is phi? Well, here's the mode expansion for our scalar field. So phi x comma t is equal to, I'm going to use oscillators that are relativistically normalized. So I've got an integral d3k. Now I want the Lorentz invariant measure. So I'll have a 2 pi cubed, then I'll have a 2 omega k. Remember what omega k is? Let's just remind ourselves of everything. Omega k is the square root of k dot k plus m squared. Good. And then we will have an e to the minus I k dot x alpha of k. And remember what k dot x is. So let's just make sure we understand everything. So k dot x is omega kt. It's a 4-vector product minus spatial k dotted into spatial position. And then we've got plus e to the I k dot x, and we've got an alpha dagger of k. And remember what it meant to say that our oscillators have a relativistic normalization. What it meant was they obeyed a commutator alpha k, comma, alpha dagger of p is equal to 2 pi cubed, and then a delta function of p minus k. And what was significant about this commutator, with the 2 omega k. What was significant about this commutator is that it's the same in all inertial frames. Whenever you want to get anything, an operator, whatever, you have to solve an equation. The equation that would solve to get oscillator operators is this commutation relation. And the fact that it's the same in all reference frames means we've set things up so that all inertial observers use exactly the same oscillators. Good. So we're making Lorentz invariant manifest. Now we're going to want pi squared. So what is pi? Well, I'm sure you remember that pi of x and t is nothing but phi dot of x and t. So we want to calculate a time derivative. Okay, where does the time derivative act? Well, there's no time dependence in the measure. So we'll have an integral d3k over 2 pi cubed at 2 omega k. And then we have the exponentials. And in fact, in the exponential, there is a t dependence because k dot x is omega kt. We've got a minus I there. So for the first term, we'll have a minus I omega k. So this is by differentiating the first term with respect to t. And then we've got an e to the minus I k dot x alpha of k. And then for the second term, again, the exponential is time dependence. So we'll get I omega k times e to the I k dot x times by alpha dagger of k. Good. So that's what pi of x comma t looks like. Now, when we come to calculate the Hamiltonian, you can see that there's 3 separate terms inside the Hamiltonian density. I'm only going to show you how to treat the first term. So I'm going to do the integral d3x of 1/2 pi squared. But once I've treated the first term and you've seen how to do it, you will easily be able to treat the remaining terms. So I'll leave that to you, Okay, so what term do we want to do? Well, we'll have an integral d3x. We will have 1/2 pi squared of x and t. Okay, this is the first term from the Hamiltonian density. Okay, to do that integral, what will we have? Well, it'll be an integral d3x. Let's not forget the 2. We'll put that over 2. And then pi times pi means we have to take this quantity with the integral d3k and all the rest multiplied by itself. So let's call the momentum that we're integrating over for the first pi, let's call that k1. So we'll have an integral d3k1 over 2 pi cubed to omega k1. And then we'll call the second momentum k2. So we'll have an integral d3k2 2 pi cubed to omega k2. And now we can put in these two brackets. So for the first one, we've got minus I omega k1 e to the minus I k1 dot x alpha of k1. Sorry, I'm squashing it up a bit. Plus, well, let's go to the next line. Plus I omega k1 e to the I k1 dot x. And then we've got alpha dagger of k1. And then we've got the second bracket, which will be minus I omega k2 e to the I k2 dot x alpha of k2 plus I omega k2 e to the I k2 dot x alpha dagger of k2. So let's look at this expression, okay? Where is the x dependence? Well, the x dependence is lurking in the exponentials. You see, k dot x has got spatial x in it. So the exponentials have got spatial x in it. The reason why I'm focusing on the x dependence is that we're going to do the x integral first. Okay, so let's make a comment on that. Whenever you want to evaluate operators like this, you should do the x integral first. So we'll do the x integral first, okay? And how many different terms are there? Well, I've got a bracket with 2 terms multiplied by a second bracket with 2 terms. So I should take the first term multiplied by the first term multiplied by the second term multiplied by the first term, and the second term multiplied by the second term. I am only going to do with you the first term multiplied by the first term. After you've seen how this one is done, you'll be able to do all of the remaining terms. So let's just do this term first, okay? And let's talk about what integral we have to do. So we'll have an integral d3x. This is, of course, the integral that we want to do. And then from the first term in the first bracket, we'll have an e to the minus I k1 dot x. And from the first term in the second bracket, we've got an e. Oh, that should be a minus. So let me put that minus in there. That should be a minus I k2 dot x. This will be minus I k2 dot x. So that's the integral that we want to do. Let's just write out these k dot x's explicitly. You know what they are. They're an omega kt minus spatial k dot spatial x. So if we just write this out, this is an integral d3x e to the minus I omega k1t minus I omega k2t. And then we've got plus I k1 dotted into x1. Dotted into x. There's no x1, so just dotted into x. And then plus I k2 dotted into x. So when we want to do the x integral, well, those first 2 exponentials don't depend on x at all. So we can pull out e to the minus I omega k1 t minus I omega k2t. And then we've got an integral, d3x, of e to the I k1 plus k2 dot x. And you know what that integral is. We've discussed it. That's 2 pi cubed times by a three-dimensional Dirac delta that's going to set k1 equal to k2. So that's the answer for doing the x integral, okay? I want you now to try to do the x integrals for all of the terms. So we just did the first term times the first term. You go for first times second, second times first, and then second times second. Once you've got an answer, start observing the next video.